Hello, this video is to help students understand and complete the Riemann sums project. Um, you should understand that we'll be approximating the area between a cubic polynomial and the x-axis between two x values, and we'll then use limits to find the exact value of that area. There are several summation properties that you should be comfortable with. We proved the last three of these by induction. So in my example, I use the function f of x equals 2x cubed minus 3x squared plus x plus 3. I chose to do it on the interval from 0 to 2 with 8 subintervals. I also chose an MRAM, which is a midpoint rectangular approximation method. It will help you visualize what we're doing if you go to the Desmos link that I've put in here, and you can type in the function under input function. If you set c equal to 0.5, you'll get a midpoint RAM, and set a and b to 0 and 2 respectively. M, the number of partitions, should be set to 8. The idea behind a Riemann sum is simple enough. It approximates the area beneath a curve by dividing the region into thin vertical rectangular strips, as shown in this illustration at right, which I copied from Desmos. The heights of the rectangles are calculated several different ways, possibly. You could use the height at the left end of each rectangle, at the right end of the rectangle, or height right in the middle of each rectangle, which is what I'll be doing. Since the interval I'm using goes from 0 to 2, and since I'm using n equals 8 subintervals, the width of each rectangle is 2 minus 0 over 8, or 1/4. The subintervals are from 0 to a quarter to a half to 3/4, etc., all the way up to 7/4 to 2. If you were calculating an LRAM, you would calculate the function value at the left endpoint of each strip. So at 0, a quarter, a half, up to 7/4. An RRAM would use the right endpoints. Since I'm using an MRAM, I'll use the midpoints, which are listed here. I want to note that the midpoints form an arithmetic sequence, with the kth midpoint being given by m sub k is 2k minus 1 over 8. So we can approximate the area of the kth rectangular strip by multiplying its height, which is f of m sub k, by its width, delta x. The area of the region is then calculated by adding up these 8 rectangles. So sum from k equals 1 to 8 of m sub k times delta x, which is the sum from k equals 1 to 8, and then here I've just calculated f of m sub k in terms of m sub k. This last term, 1/4, is the width of each rectangle. We can break up this expression using the summation properties above and substituting in the formula for m sub k given here. And I get the following. I pull the 1/4 out from every term. I can then pull out also the coefficients 2, -3, and the constant 3. Now, I bring out the denominators, 8 cubed, 8 squared, and 8, and I get the expression that we can see here. I have also expanded out 2k minus 1 cubed for you right here. If you keep separating the summations using the first 3 rules above, you'll gradually get these expressions. And then expanding using the last 3 of the summation rules I gave at the beginning of this document, you get the following expression. It's completely okay to use a calculator at this point. You'll get the following expression here, which comes out to 7.96875, or 255/32, which is exactly the answer you get in Desmos. For the final part of the process, calculating the area as n approaches infinity, you let the width of each subdivision be 2 over n, because the length is 2 and there are n subdivisions. The kth midpoint is now 2k minus 1 over n, but everything else is the same, except now we sum from 1 to n instead of 1 to 8. The process is almost identical, and eventually we get down to these formulas. And in these, I want you to remember that in a rational expression, if the degree of the top and the degree of the bottom are equal, the limit is the ratio of the leading coefficients. If the top has lower degree than the bottom, the limit is always 0. So as a result, we get limits of 8 and minus 8 and 2 and 6. So in other words, 8 minus 8 plus 2 plus 6, or 8. And that is in fact the exact area between 2x cubed minus 3x squared plus x plus 3 in the x-axis on the interval 0 to 2. In Desmos, you can confirm it by letting the number of partitions go very, very large. I set it to 5,000 in this case, and notice that the area that I get of 7.9999992 is very close to 8, which is what I got by taking the limit.